Next, we'll look at two more examples of parameters in permutations. Again, just to gain some comfort with the basic method and also to get more familiarity with properties of permutations. And there's many, many other examples in the book. We're picking 4 parameters of permutations, and there's another 5 or 6 or more in the book. So say you want to know how many 1 cycles are there in a random permutation of size n. For 2, the average number of 1 cycles is just 1 because the permutation has 2 1 cycles, has 2, and the one that's a 2 cycle has 0. So the accumulated cost is 2, and divide by 2 we get 1. For 3, we have either 3 1 cycles, which is 3 to the accumulated cost. We have 3 of them that have 1 1 cycle, so that adds another 3 to the cost. So again, the total is accumulated cost is 6. And then there's 6 of them, so the average is 1. And you might start to see a pattern, and sure enough, for permutation of size 4, the total accumulated cost, and you can count through it here, there's 24 1 cycles in all these permutations, and there's 24 permutations, so the average is 1. So we're going to expect our result to show that the number of 1 cycles, expected number of 1 cycles in a random permutation of size n is 1. And to show that, we're going to use precisely the same construction that we used for counting cycles. So again, we put p plus 1 into every position in the cycle. The difference in the analysis is if the original perm has cyc 1 of p1 cycles, how many are there in the set of constructed firms? Well, you have the same equation to start out with, that is, whatever number of 1 cycles there are in the original, there's p plus 1 times that in all of these, but then we have to adjust to add the new 1 cycle when we added our new element to make it a 1 cycle. And then we have to subtract off for every 1 cycle that was there, in this case the 2, we knocked it out by making it into a 2 cycle in one of the perms. So we have to subtract off cyc 1 of p. So that gives a slightly different formula. The number of 1 cycles in the set now is p times cyc 1 of p plus 1 instead of p plus 1 times cyc 1 of p. So just that plus 1 is the difference between this equation and the one that we did for left to right minima and for cycles. So let's look at what that happens to the analysis when we do that. So CGF, and then we apply the construction, and again, the only difference is there was p plus 1 before, and now it's p. So now we don't have the ability to use the factor of p plus 1 to knock out the factor of p plus 1 in the denominator of p plus 1 factorial. So we have to knock that out in a different way, and the easy way to do that is to just differentiate. So if we differentiate z to the p plus 1 over p plus 1 factorial, the p plus 1 comes down and cancels, and we just have z to the p over p factorial. And then our 2 terms are immediate. And now the second one is just the EGF for permutations is 1 over 1 minus z. In the first one, the p cancels out, and so that is just b prime of z. So if you take the derivative of b of z, if you look in the upper left, then first formula, the p cancels out with the p factorial in the denominator, and then we're just left with an extra factor of z. So it's z p prime of z. And then plus 1 over 1 minus z, and that's our answer. So now we have a differential equation, b prime of z equals 1 over 1 minus z squared. And that's easy to solve. It's just 1 over 1 minus z. And the coefficient z, the n in that is 1. So average number of 1 cycles in a random permutation is 1. Again, very straightforward. Each step takes a little bit of experience to know when to differentiate and how to rearrange terms, but usually these types of arguments are quite elementary. For example, in our students and rooms problem, everybody goes back to a random room. What's the average number of people who wind up in their own room? Well, what we just proved is that it's 1. Now, just to test yourself, your understanding of this method, it's worthwhile maybe to take the time to try to figure out the expected number of 2 cycles in a random permutation of size n, or then generalize that to the expected number of r cycles in a random permutation of size n. The answers are 1 over 2 and 1 over r. And you can, by solving these problems, you can you get a little practice with manipulating these kinds of equations. As our last example of studying parameters and permutations, we'll look at inversions. An inversion in a permutation is a pair that's out of order. That's a little bit imprecise. A better way to look at it is to say it's the sum of for each entry, we sum up the number of elements that are larger and to the left. So for example, in the top right corner, 1, 2, 4, 3, the only pair that's out of order is 3 and 4. 3 has 1 larger element to its left, the 4. All the rest of them have 0 larger elements to the left. The one below that, 2, 1, 4, 3, has 2 inversions. 1 and 2 and 3 and 4 are out of order. 1 has 1 larger element to its left. 3 has 1 larger element to its left. The one below that, 3, 1, 4, 2, that one has 3 inversions because 1 has 1 larger element to its left, the 3, and 2 has 2 larger elements to its left, the 4 and 3. And again, for every one of these permutations, we have written down off to the side the number of inversions. If you add all those numbers up, you get the accumulated cost. For 3, the accumulated cost is 9, so the average number of inversions is 1.5. For 4, the total accumulated cost is 72, so the average so the accumulated cost is 72, and the expected number of inversions is 3. That's the quantity we want to study, the number of inversions. An application of this is to analyze another elementary sorting algorithm called insertion sort. That's also the method of choice in some situations. We can read about it in algorithms. Understanding its performance for random permutations is useful in practical situations. So what insertion sort does is it goes through the array, and for every position I, its job is to keep all the elements before I in sorted order. And the way that it does that is when it gets a new element, it exchanges it with all the larger elements to its left. So in this case, when I equals 10 and it's pointing at the m, it knows that everything to its left is already sorted. But looking at the current element, its elements to its left is larger, so we exchange. And we keep exchanging as long as the element to its left is larger. So m is still, O is larger and n is larger. And when it gets to a point where the elements to its left is smaller, then it's inserted into its proper place in the array. So that's known as insertion sort. The exchanges put the current element into place among the elements to its left. And so the cost of this sort, or number of exchanges, is going to be the number of inversions in the permutation. So we want to know how many inversions there are in a random permutation in order to understand insertion sort. So for example, insertion sort is often used in practice as when you use quicksort, a recursive method like quicksort or merge sort. When the files get small, those methods are less efficient than insertion sort. So you want to switch to insertion sort. You want to analyze the size at which you should switch to insertion sort. You have to be able to answer this question. So that's insertion sort. So what's the construction for inversion? So now we're going to use a different construction. I didn't mention this one as one of the basic constructions for analytic combinatorics, but it's got the same transfer theorem and so forth as the star. And it's just an indication of the kind of freedom that we have in trying to understand combinatorial objects. So in this construction, we're going to create a permutation. I use a 6-pointed star. A permutation of size n-1, I'll create a permutation of size n by inserting n in every possible position. So here the 7 goes from the rightmost down to the first position. Then there's no renumbering involved. They all have the labels from 1 to 7 when you do that. So now you notice that as we move from left to right, we add one more inversion. The first one, there's no additional inversions, it's the same number of inversions. But then each one, as we move down, everybody to the right of 7, it gets one more inversion added because now 7 is to its left. And so we can calculate, again, as before, if we know the number of inversions in the original permutation, then we know the number of inversions in the set of constructed permutations. And it's, there's all the inversions in the original are still there in the constructed permutations, but then we have all these additional inversions, 1 plus 2 plus 3 up to size of p, which is size of p plus 1 times p over 2. So that's a number of inversions in the set of constructed perms. Now we're going to use that equation in our typical construction. So now our accumulated generating function is on inversions. And again, rearranging the size of the sum by size of p plus 1 and grouping those together, that gives that equivalent equation that we can now simplify. It's got two terms. In the first term, the p plus 1 cancels again against the p plus 1 factorial. In the second term, the p plus 1 and both in that one also the p plus 1 cancels. So the first term is just zb of z. In the second term, if you group by k, it's just kz to the k, because there's k factorial of size, and there's an extra z thrown out in the 1/2 from p plus 1 over 2. So that simple equation, solve for b of z, is zb of z plus 1/2. That generating function is just a derivative of z to the k, so it's z squared over 1 minus z squared. Now solve for b of z and get another factor of 1 minus z. And again, that's one of our most elementary generating functions. Coefficient of z to the n in that is the average number of inversions is n times n minus 1 over 4. So that's the fourth derivation, and that's enough. And again, if you want many more, there's many more in the book. Again, that checks against small values. There's lots of properties of permutations that have been studied in classical combinatorics and that can be handled in a similar manner. So for example, a rise in the permutation is when the value goes up. A fall is when the value goes down. A peak is when the value goes up and then down. A valley is when the value goes down, then up. A run is if you have successive values going up. Left to right minima, we already talked about, and increasing subsequence is some subset of the permutation where they go up. And all of these properties can be handled in a similar manner. And again, the book contains several other derivations and wouldn't be productive to cover in lecture. So those four indicate an approach towards studying parameters of permutation that's effective. And those that we looked at have actual applications to understanding the performance of important algorithms in practical situations.